Thank you, Chair, and thank you, organizers, for giving me this opportunity to present this work. So what I'll be talking about today is quantum spin glass criticality, particularly which arises when there is a competition between frustration and disorder. So let's get started with some simple things. So we are all aware of conventional magnetic phases. So for example, on the left-hand side, you see a ferromagnet, which is characterized by a long-range order, and in the Landau sense, you can write down a order parameter. In this case, that's just your total magnetization, which is just the sum of all the local moments in your configuration. On the right-hand side, you have an antiferromagnet. Of course, the total magnetization here is 0, but nevertheless, there is an ordered pattern. And in fact, you can again quantify this ordered pattern by a suitable order parameter, which is the staggered magnetization in this case. Which is essentially the sum of the local magnetizations of these red spins minus the local magnetizations sum of all the blue spins. And in general, you can do it for any spiral state with an appropriate ordering wave vector. That is what we learn in the Landau sense, and you can characterize ordered phases of matter. But then when you have frustration, and this whole session is about frustrated magnets, and we saw in Professor Yusuf's talk also in the morning, he nicely introduced frustration in the system. It gives rise to various exotic magnetic phases in general. And in particular, you can have exotic phases like quantum spin liquids, where there is no magnetic long-range order, and there could be deconfined spin-ons and emergent gauge phase and so on. All right, but my talk is not going to be about such exotic things, but relatively simple stuff. But frustration will play an important role nevertheless. Now, apart from frustration, in real materials, you cannot escape disorder, and disorder is ubiquitous. And there are various kinds of disorder one can imagine. So if you have a perfect crystalline lattice, as a theorist, this is what we imagine and this is what we desire. But in a real material, there are always some site defects. Certain magnetic ions could be replaced by some non-magnetic ions, or there could be some vacancies. Or if there are ligands or some intermetallic molecules, or let's say ions, which are essentially responsible for exchange interactions between your actual magnetic ions, they could be replaced by some other dopant or some other impurity in the system, and that could inhibit the super exchange path among your magnetic ions. And what that will lead to is a bond type of a disorder. So there are roughly two kinds of disorder. There could be many more types. But in terms of magnetism, you could have these vacancies or site defects, or you could have these bond disorders, meaning your exchange interactions could be affected because of such impurities which are sitting on interstitial sites. Right? And this disorder in magnets typically is not very serious, particularly if you have collinear magnets like ferromagnets or antiferromagnets on unfrustrated lattices. Then these disorders are known to be not so detrimental. They will essentially keep your long-range order as it is. Of course, there is disorder-related physics of mode localization and broadening of your spectral features in your inelastic neutron scattering data, but overall the magnetic phase still survives even in the presence of such disorders for simple magnetic ground states. However, if you have non-collinear magnets and if there is a disorder present in such systems, then these disorders can have serious effects. Again, depends on what kind of disorder you have. If you have a site dilution or a vacancy, then again the non-collinear magnetic texture is typically stable against such impacts. Whereas if you have a bond disorder, then it is known to be very detrimental and can immediately destroy your non-collinear long-range magnetic order. Right? And there is of course other possibility, especially in two-dimensional quantum magnets, that you can have phases like random singlets forming because of very strong impurities or strong disorder in the system. So what this talk is about is another possibility where in the presence of frustration and disorder, you may also encounter a quantum spin glass state. Now, just to give you a pictorial representation of what a quantum spin glass is, just like we saw pictures for ferromagnet and antiferromagnet, you can characterize them using some ordered pattern, and you can easily write down some ordering wave vector for this. For a spin glass, of course, the magnetization is 0 and there is no particular pattern or arrangement of spins, so there is no usual order in the usual sense like we do for other spiral ordering. But nevertheless, these spins are frozen, and they are frozen in random directions. So although the net magnetization is 0, if you go on any particular side, the expectation value of the spin operator is non-zero. So in that sense, it's different from a paramagnet, of course, where also the total magnetization is 0. But there, the locally every spin operator expectation value is 0, either by thermal or quantum fluctuations, right? So that's essentially the phase that I will be interested in, and I'll describe a particular microscopic model where you can realize such a quantum spin glass. And what I'm interested in is quantum phase transitions of such quantum spin glasses. Now, spin glasses is a very old subject, and classical phase transitions of spin glasses have been very well studied right from 1960s or so, and the thermal transitions are very well understood, or to some extent very well studied, both experimentally and theoretically. But quantum phase transitions of quantum spin glass is relatively less understood. At least from the theory perspective, there is limited work that is only using either Ising spins or some all-to-all sort of models. And with continuous symmetries, particularly using Heisenberg spins, there is relatively less work, exceptionally only in the context of Sachdev model, where we know that the ground state is also a quantum spin glass. So that's the motivation, and that's the sort of the theme or the aim of this work, to sort of look for examples and study these quantum phase transitions in slightly more detail. And there are various possibilities of what sort of quantum phase transitions that you may have from a quantum spin glass. So there are at least 4 possibilities that I can think of. Probably there are many more. So a quantum spin glass can have a quantum phase transition into an ordinary ordered magnet, some ferromagnetic or some non-collinear spiral. There is also a possibility that there is a quantum phase. There could be a quantum phase transition between a quantum spin glass and a quantum spin liquid. This can certainly happen in frustrated magnets, where in clean systems there is a quantum spin liquid, and you have disorder in such systems. The other possibility is a quantum spin glass and a trivial paramagnet quantum phase transition. And another possibility is a quantum spin glass and a random singlet phase transition. So there are various possibilities, and to our knowledge, I don't think all these phase transitions have been studied in great detail. And I don't mean to, of course, solve this entire problem, but what I will be focusing on is this particular type of quantum phase transition between a spin glass and a trivial paramagnet, and particularly in a lattice system in a realistic model. So this is a work done together with Matthias Wojta, who is at TU Dresden. So let me jump onto the model directly, because it's a relatively simple model. So this is basically a bilayer triangular lattice Heisenberg model. So you just take 2 copies of triangular lattices and stack them together, and each lattice side is a spin half, and you just couple these 2 layers antiferromagnetically. So these blue bonds are all Heisenberg interactions with antiferromagnetic in nature, and all the red bonds, both in the layer 1 and the layer 2, are again nearest neighbor Heisenberg interactions, right? And this is not some theorist's dream, but there are actual materials which realize triangular lattice geometry, and in fact in a layered fashion. So there are bilayer possibilities of such triangular lattice antiferromagnets, and these are sort of set of materials. And as far as I know, I think few of them, there are already certain experiments either in the field, or also some neutron scattering experiments have been performed. What would be interesting would be to do experiments on these materials under pressure, because then you can tune actually this ratio of the interaction K versus G, and that will play an important role, as you will see in the talk. So let's first quickly see what are the different phases that can occur in the clean limit. So if the blue bonds are dominant, and as I said, these are antiferromagnetic interactions, and the red bonds are very weak, then essentially you have 2 spin half interacting antiferromagnetically. So the ground state is simply a product state of such singlets. So this is a trivial paramagnet in that sense. It does not break any lattice symmetry, no spin rotation symmetry is broken, anything. So it's just a trivial quantum paramagnet with such a singlet ground state. And the excitation is on any given dimer site. You break the singlet, and it can go into one of the 3 triplet states, right? So you have a singlet triplet excitation on any given dimer site. And such triplet excitations, the quasi-particle corresponding to them, are what are called as triplons or triplet operators. And this can be worked out as bosonic quasi-particles. The other extreme possibility is when the red bonds or the red interactions dominate, meaning that the interlayer interaction is very weak and these are basically sort of decoupled layers. Then this is your usual Heisenberg antiferromagnetic model on a triangular lattice, and here we know that the ground state is the 120-degree Nell ordered phase. So this is just the top view of one of the layers. There's another layer exactly below that with the same opposite configuration with 120-degree order. Here again we know what sort of excitations you expect. So here you have the Goldstone modes because of continuous symmetry breaking of your spin rotation symmetry. So you have the usual Mexican hat picture where the magnons are essentially these gapless excitations, and apart from that you also have this amplitude mode, which is a gapped excitation. That's basically your order parameter fluctuation or magnetization fluctuation on any given dimer site. So this is basically the clean limit picture, and you clearly see even in the clean limit there is a phase transition as you tune this ratio of k by j. When k by j is larger, you have this long range magnetically ordered phase 120-degree, and when k by j is small, you have this trivial paramagnet, dimer quantum paramagnet. Now we are interested in this model in the presence of disorder, namely two types of disorder that I talked about, either vacancies or sites or bond disorder. But here I'm going to focus on bond disorder, and that's what is going to give rise to interesting stuff. And again, from a theoretical perspective, there are two ways I can model this bond disorder. One is by using sort of a bimodal distribution, whose picture I have shown here, meaning that compared to the clean limit, I select a few bonds whose interaction strength I flip compared to the clean limit. So all the black bonds in this picture are the clean limit bonds whose interaction strength is k, and all the red bonds are the defect bonds with some probability p, and that interaction is given by alpha times k, where alpha is some number between 0 and 1 or even greater than 1. And similarly, you can have disorder in the perpendicular direction as well, where the interaction strength is between the two layers. So that picture I'm not shown because I can't draw that. And the other possibility is you can also model the bond disorder using a box distribution, meaning that instead of selecting a few defect bonds with some probability p or p prime, I have a continuous range of interaction strength between k minus delta k and k plus delta k, and each bond takes a value in this box distribution with some probability, with this probability. So all the results that I'm going to show will be for such box bond distribution, but the physics is the same irrespective of what distribution we use, and I'm going to focus on this. All right, and just one technical slide about how this computation is done. Remember that in the phase when the blue bonds were dominant, I had this singlet triplet physics. So I can use the basis of singlet operators and triplet operators and write them as bosonic quasi-particles called triplons. So you can express your spin operators in terms of this triplon operators, and one can show that using suitable Hilbert space rotation, even the 120-degree Nell ordered phase or any magnetically ordered phase for that matter can be represented in such a generalized triplon form, operator form. So these T operators which I have denoted in red are those generalized triplon operators on any given dimer site, and all the black stuff that I have written here, these are essentially some matrix elements that you don't have to worry about. So in the trivial paramagnet, these matrix elements are just 1/2 plus or minus something. In the ordered phases, these are more complicated, and particularly in the presence of disorder, this will be even site dependent, and this have to be solved self-consistently in a mean field fashion. So essentially what the problem boils down to is an interacting boson problem where you have some non-interacting boson plus interactions, and what we are going to do is treat disorder exactly, but we are going to make an approximation that we are going to neglect boson-boson interaction. And this is what we call as the harmonic approximation, and this is justified using various means, and in just two words. Either you can technically show that all the boson-boson interaction, they are suppressed, and those self-energies are suppressed as 1/d, where d is your spatial dimension. So in some sense, in infinite dimension limit, this is actually exact, and all the quantum corrections can be arranged systematically in powers of 1/d. Another way to see that is your self-energies or your quantum corrections are directly proportional to the your quasi-particle density, and you can show that this quasi-particle density in such problems is pretty actually very small, about less than 10%, and so these interaction terms do not qualitatively change any of the physics. But nevertheless, it's very challenging to treat disorder as well as interaction together. So we are going to make this approximation. And just for people who are in this field, here you have 3 flavors of boson. So it's not just a single flavor of boson and interaction between bosons, but you actually have 3 flavors of bosons where you have this non-interacting stuff and there is interactions among them. So even at the non-interacting level, these flavors are coupled. So this is a fully coupled model of 3 flavors of boson. So you have to sort of diagonalize 3 n modes for an n cross n system. All right. So once you do that, then we look at observables. So one standard way to diagnose magnetic order is to look at static susceptibility, and you can extract what is the order parameter, right? So for the 120 degree Snell phase that I was showing on this triangular lattice, the ordering wave vector is this q, which is 4 pi by 3 by 0, which is on a honeycomb Brillouin zone. It's the corner of your site of the Brillouin zone. And the staggered magnetization or this 120 degree Snell ordered parameter is essentially given by this. Similarly, you can also write down a spin glass susceptibility, which is again some spin-spin correlation function. And the spin glass order parameter is related to the spin glass susceptibility in this way, which is called as the Edwards-Anderson order parameter. And we are going to use this to quantify the results that we get. All right. So firstly, one can show that these bond disorders that I was talking about in the intralayer directions, these are very detrimental, and these are relevant perturbation in an RG sense because they are very strong dipolar perturbations. And any infinitesimal small number of such defect bonds immediately destroys this 120 degree Snell ordered phase in favor of a quantum spin glass, which you can see, for example, here, where I have plotted the spin susceptibility as a function of momentum around the ordering wave vector. So here 0, 0 corresponds to the ordering wave vector q that I was showing. Sorry for the notation being slightly different. So in the clean limit, you would have just expected a delta function peak here because that corresponds to your magnetic Bragg peak. But because of disorder, you have broadening, and you can quantify this broad feature. The full width half maximum of this Lorentzian shape essentially gives you the inverse correlation length. And what you can show is if you do a proper finite size scaling of this inverse correlation length, then in the thermodynamic limit, this does not vanish, meaning that you don't have a true magnetic long range order of the type of 120 degree Snell phase, and it is immediately destroyed in favor of a quantum spin glass. And now you can also calculate the quantum spin glass order parameter, which I defined earlier. And as a function of this tuning parameter now that we have in the problem, namely the interaction strength within the layer versus the interaction strength between the 2 layers, you see that the quantum spin glass order parameter actually systematically decreases as you go towards the quantum paramagnetic phase. And this is what then leads to the quantum critical point and the quantum phase transition between quantum spin glass and the trivial paramagnet. So what is shown here in the inset is as a function of the disorder, which is on the y-axis, and on the x-axis is this tuning parameter k by j. What is the phase boundary between the quantum spin glass and the dimer quantum paramagnetic phase? So in the clean limit, it is at some value 0.33, which is 1/3 in this mean field calculation. And as you increase the disorder, you see that this phase boundary shifts towards the dimer quantum paramagnetic phase. So schematically, this is the phase diagram as a function of disorder on the y-axis and this tuning parameter. Exactly at 0 disorder, you have a paramagnet to 120 degree Snell phase kind of a quantum phase transition. But immediately when you have disorder, you have this quantum spin glass to quantum spin glass phase transition. And it's the vicinity of this is what we are interested in. So firstly, of course, you have the usual disorder physics and sort of inhomogeneous local magnetization that emerges because of this disorder. So what is plotted here is actual snapshot of certain disorder realizations, and each point is essentially a lattice point showing the local magnetization of the spins. So from right to left, you're approaching the quantum critical point. So on the right hand side, you see this inhomogeneous distribution of the local moments, and there is some mean value to it, and I'll quantify it in a minute. But what you see is as you approach the quantum critical point, you start seeing these puddles of local magnetization, meaning that there are these Griffith's phase sort of related physics, as well as this inhomogeneities that emerge in the system. So there are lots of regions where the magnetization is essentially zero, and only local islands of some local magnetization emerges. So you can quantify this by actually plotting the probability distribution of these magnetizations. And what one can see is for weaker disorder, the magnetization is not very broad. So of course, because of the disorder, there is no sharp peak, there is no single value of your local moment, but there is a distribution, and it has a particular width, but these are not very well spread. And as you go towards the quantum critical point, of course, the mean value starts decreasing, and eventually it goes to zero at the quantum critical point. However, if you increase the disorder strength, something very drastic happens, and you see that the moment distribution function is extremely broad and asymmetric, more importantly. And particularly, this asymmetry is very strong as you go towards the quantum critical point. So the glassiness, the Griffith's physics is sort of embedded in this highly asymmetric and broad distribution, and particularly for this black curve, which is very close to the quantum critical point, you see a very long tail. So which means that as you approach quantum phase transition, there are regions where you have very small moments, but there are also regions where there are actually very large moments. So all possible values of moments are allowed. And you see that this scale goes from 0 to 0.5 in some normalized sense. And even close to the critical point, there is a finite probability of finding moments, which is about 0.2, which is just half of the saturated moment size, whereas the mean value is extremely close to 0. Right? Log normal. So in fact, if the disorder is very weak, is practically very close to Gaussian, in fact. And in fact, you can also quantify, I'll finish very quickly. You can also quantify the energy landscape, which I will skip. So you can actually quantify how rugged the energy landscape is, which is one of the characteristics of quantum spin glasses. But let me first talk about chirality. So because we know that the clean limit 120-degree null phase is a coplanar state, one of the effects that the disorder has is actually to make these spins non-coplanar, and this is what is captured by this scalar chirality. And what we have plotted here is again the probability distribution of this scalar chirality, and you immediately see that as you increase disorder in the system, the chirality is non-zero, and immediately the spins start becoming non-coplanar. And in fact, it is sort of counterintuitive that deeper inside the quantum spin glass, actually the non-coplanarity is stronger, whereas if you go towards the quantum phase transition, the spins configuration again starts becoming coplanar, more coplanar, which again you see here because the blue curve is corresponding to phase when you are very deep inside the spin glass, whereas the black one is where you are closer to the quantum phase transition, and it peaks around 0. So it's more coplanar than the spin glass. You can also quantify using vector chirality how non-collinear your spins are. So in the clean case, again, if you calculate this quantity and extract the relative angle between your nearest neighbors, it is exactly 2 pi by 3, which is corresponding to your 120-degree null ordered phase. Now, if you have disorder, one can quantify what happens to this non-collinear nature of the spins, and something very interesting happens. So as a function of disorder, if you have a very weak disorder, then again the relative angle between the spins still remains about 2 pi by 3. There is of course broadening, as you would expect as a function of disorder, but more or less it's close to the same 120-degree ordered phase. But if you increase the disorder very strongly and particularly drive the system towards the quantum phase transition, you see something very drastic. You see that the angle probability distribution starts peaking around 0 and pi, which means quite counterintuitively, you start with a non-collinear state, you add disorder, so this is a very frustrated system, but as you approach critical point, actually the frustration is released and the glass becomes weaker and the spins. It's not a dimer model in that sense, probably what you're thinking. Yeah, it's just the propagation of the spin 1 excitations in the system. So I don't think it has this flat band physics that will rise. Of course, if you have strong triplon interactions, then certain, so to say, regions in your momentum space will have flat energy dispersions, which we have evidence for and which we have calculated in some other context, but not of the type that you are saying.
Okay, unfortunately, we have ran out of time, so let's close the talk by thanking the speaker.